Hi, in the previous video we looked at the Eikonal equation and tried to get some intuition as to what each term means. In this video we're going to take the Eikonal equation and be a little bit more mathematical about it. So it's written right here. Let's multiply both sides by v. We get v of r times absolute value of the gradient of the travel time function equals 1. So let's think about the type of quantities we have. V is the speed of light, right? It doesn't tell you about the direction of the light. It just tells you how quickly the light is going wherever you evaluate the function. The travel time, or the gradient of the travel time function, that is a vector. We saw that in the last part. It actually defines the direction of the rays of light. Now, in this expression, we're taking the absolute value of this function. So we're actually throwing away the vector information, the direction of this, and all we're left with is a scalar. And on the right-hand side, we have the number 1, which of course is a scalar. And that makes sense since a scalar times a scalar equals a scalar. But the point of this part is to consider what happens if we don't take into account this absolute value. Let's say we remove this absolute value function. Well, by doing that, we are introducing a direction, the vector describing the direction of the ray of light on the left-hand side. Let's do that. Remove the absolute value. We no longer have a scalar. We're going to have a vector. And on the right-hand side, instead of just the value 1, we're going to have the value 1 as the magnitude, but it's going to be in a certain direction, which is the same as the direction on the left-hand side. So instead of the value 1 and a scalar, what we're going to get is a vector. Let's see, a vector, and it's going to be a unit vector. It's going to have the magnitude 1, but the same direction as on the left-hand side. I'm going to leave that blank for now. But that's what we're going to come back to. So, I mean, these equations are valid for any position r that you choose. But we want to apply them to the path of a single ray of light. So I'm going to redefine the meaning of r into being positions along the ray of light. And I'm going to do it with a parameter that we call s. So let's just write this down. So we're defining r of s as all points along ray of light. Now we have some choices as to what s can represent. S here is, just a parameter. It can, for example, we can use it to represent the time that the ray spends to travel. So for example, if we say s equals 1 second, then r of s is the position of where the light is after 1 second. On the other hand, we can also say that s is the distance traveled. So for example, if s is 1 meter, then r of s is the position of the light ray after it has traveled 1 meter. And I'm going to choose the last choice here. I'm going to say that s is the distance traveled by the ray of light. So what we have here is that, if you just look at the small part of the ray, a very short part of the distance traveled by the ray, we have that this small part of the position is going to be equal to a small change in the parameter s. Let's do the absolute value so that we have a scalar on the left-hand side and a scalar on the right-hand side. And just for being brief, instead of writing r of s all the time, I'm just going to define a new notation where r is the same, or it means the same by notation as r of s. So what we have is dr equals ds. So let's make a simple 2D vector example of this. Let's say we have a ray of light travels from this point and up to this point. Let's draw it like this. Small part of a ray. And from the starting point, the parameter has some value, s1, and the endpoint, it has some other value, s2. And we can describe the starting point as a vector from some point, which is the 0. Let's say it goes like this. And this vector is r of s1. And the second point, not surprisingly, is also r of s2. And the difference between these two vectors, r of s2 to r of s1, we're just going to write that as dr vector. So the path that this green ray is traveling, we can describe the distance of this, we can describe the direction of this by writing we can describe it by a unit vector. And the unit vector of that aligns with dr is pretty simple, right? We can find dr, and if we divide dr by the length of dr, well, then we get a unit vector that is pointing in the same direction of dr. Okay, I'll write unit vector. And from the definition that we had above here, since absolute value of dr equals ds, we can say that this is the same as dr over ds. And now, I'm sure you understand the next step here. We can make this connection with the Eikonal equation from before. So what we get is v of r times gradient of travel time function equal to dr over ds. This is known as the kinematic ray equation. And the way we can describe it is that we can say that the wave front gradient, that is the gradient of the travel time function, it defines ray direction. In the next video, in part 3, we're going to look at how we can take this kinematic ray equation and transform it into what we call a set of ordinary differential equations, or ODEs. And what this means, ordinary differential equations, is an equation on the form where on the left-hand side we have the derivative of some variable with respect to another variable, which we're going to call s, when that is equal to some expression in terms of both s and the variable y. So that's an ordinary differential equation. if we consider y here to be a vector, right, it contains more than just a single variable, then we can call this a set of ordinary differential equations. And what's the reason for doing this? Well, there's already exists a lot of software, a lot of libraries and tools that help us solve this. So as long as we formulate our problem into this format, then we can take this problem and use already existing tools to do the computations. And these tools are known as ODE solvers, and that's what we're going to be using. But before that, in the next part, which is going to be fairly math intensive, in the next part we will show how we can derive those ordinary differential equations. If you like the video, please like and subscribe. Thanks.